In this video, you're going to learn how to determine the length of an arc. To start with, let's look at the perimeter of a circle. Now, we have a circle here, and you know that the distance, say if I start at this point on the circle, and I cover the whole distance round the circumference back to the point I started with, the whole distance covered has a length, is essentially, and it's equal to the perimeter of a circle. It's given by this formula 2 pi r, where r is the radius of a circle. So r is the radius of the circle, and pi is just a number. It's actually approximately 22/7. So the radius of a circle is just the distance from the center to any point in the circumference. So that's the radius of a circle. So from the center to any other point on the circumference, that length, that distance, is the radius. So determining the perimeter of a circle is a simple problem. Now, an arc is just this curved line formed between any 2 points. And you can think of it as the curved line formed between any 2 points on the circumference of a circle. That's an arc. So I'm just showing you different arcs along this circumference. Now, an arc will have a distance, or a length rather. An arc will have a length that's much less than the perimeter of the circle it's formed on. So think about it. If you start at this point here, and you go around the circle and you come back to this point, the distance you've covered, or the length, is obviously going to be more than the length when you just go from here to here, or from here to here, or from here to here, right? So if you just consider the circle, and you consider me, say, cutting the circle at this point to give something like this, essentially something like that, which I can straighten out to give a straight line. So something like this. Like I mentioned earlier, the distance from here round along the circumference back to the original point is equal to the perimeter of the circle. Now I just cut that same circle and I've gotten this straight line. The length of this straight line has to be equal to the perimeter of the circle, because this straight line can be curved back to give the original circle. Let's consider a couple of questions related to what you just learned. So the first one says, or asks for the perimeter of a circle that has a radius of 4 centimeters. Centimeters because this is a unit of length, and the perimeter of a circle is a length. I just showed you could cut that circle and you can have a straight line. So you're more familiar with lengths as used with straight lines. You saw that. So we know that the perimeter of a circle, if I call that P, is equal to 2 times pi times the radius of the circle. So what is the perimeter of a circle that has a radius of 4 centimeters? So now we're told that the radius of the circle is equal to 4 centimeters. Now, you want to know what P is. You want to be able to say that P is equal to something. 2 is a number. Pi, you know what pi is, 22/7. And R is 4. So we know what, well, we essentially can simplify this right-hand side to get a number, a numerical value for our perimeter. Pi is 22/7. Therefore, the perimeter is equal to 2 times 22/7 times 4. That means, well, 4 centimeters. That means our perimeter is equal to 44/7 times 4 centimeters. And that means that our perimeter is equal to 25.14 centimeters. So the perimeter of the circle is approximately 25 centimeters. Now to question 2, which asks for the radius of a circle that has a perimeter of 44 centimeters. So this scenario is slightly different. you're told that the perimeter of a circle is equal to 44 centimeters, and you're required to find the radius of that circle. So you're given something, you're required to find something. So you're going to have to use an equation that relates these two things, or in some cases, a number of equations that eventually relate these two things. But we only need one equation to relate the perimeter and the radius of a circle. And that equation is as follows. The perimeter of a circle is equal to 2 times pi times r, 2 pi r. The perimeter is known. Pi is known as 22/7. 2 is a number. There's only one unknown. So all we have to do is make the radius r the subject of this equation. And if you struggle with changing the subject of a formula, all you have to do is just see the algebra course, and there you find a video that covers that topic in detail. So to change the subject of this equation, so I'll just write it again. P is equal to 2 pi r. What you want is the radius on the left hand side, so I can just start by saying 2 pi r is equal to p, and I can divide both sides by 2 pi. So r is equal to p divided by 2 pi. Or I can do it in stages and say, well, pi r is equal to p over 2. So I'm dividing both sides by 2 first. And now I'm dividing both sides by pi. Dividing both sides by pi. Dividing this side by pi is the same thing as multiplying by 1 over pi. So pi here, 1. So I have r is equal to p over 2 times 1 over pi, which is p over 2 pi, which is the same thing I have here. So I now know that the radius of this circle is equal to the perimeter, p, divided by 2 times pi. What's the perimeter? It's 44 centimeters. We have 2 times pi. What's pi? 22/7. So what I have as my numerator, 44 centimeters. As my denominator, I have 44/7. So my denominator is 44/7. My numerator is 44 centimeters. Now this can be written as 44 centimeters divided by 44/7, right? And you know, from primary school maths, you can change this above expression to 44 centimeters times 7 over 47. 7 over 44. So in order to change the division sign to multiplication sign, all you have to do is take the reciprocal of this fraction we have here. That gives 7 over 44. 44 here 1, 44 here 1. So what you get is 7 centimeters. So essentially, this is equal to 7 centimeters. Alternatively, you can simplify this using a calculator. So our radius, the radius of a circle whose perimeter is 44 centimeters, is 7 centimeters. Now I'm going to focus on the theme of this video. We're trying to determine arc lengths. We're trying to determine the length of arcs. And you can easily understand where actually there's a formula for it, and you can understand where it comes from by thinking of the following. If you think of the full circumference of a circle as a length that corresponds to an angle of 360 degrees. So think about it. I'm moving about, imagine there's some central point here, and I start here and I move about this point, essentially form a circle. But in essence, I've traversed an angle of 360 degrees. If you think about it, a complete revolution, 360 degrees. So I started at a point and I moved a complete, I just covered an angle of 360 degrees. That's a complete revolution. And that's essentially corresponds to forming a full circle. That means the circumference of a circle. So there's no point saying the circumference of a circle. Now, imagine I have the same central point, but I don't cover an angle of 360 degrees. I cover some small angle. And that angle is given by this angle here. So this is probably, say, an angle of 100 degrees, for instance. This angle I just covered by moving from here to here corresponds to this arc from A to B, this arc AB in blue, right? Whereas me covering an angle of 360 degrees when I move from here, call this A, round and back to A to point B. So B and A coincide in this case. So what I'm saying is an angle of 360 degrees corresponds to the circumference of a circle,
while an angle that's less than 360 degrees corresponds to an arc.
And in this case, we have the arc AB corresponding to an angle of 100 degrees. What we want to do is determine the length of arcs, and you're going to use the idea of an angle formed during a rotation being something that corresponds to the length of the arc formed during that rotation. So that's the main idea. So let's move on to the next part of this video. So here I have a circle broken down into sectors. As you can see from the sectors, I have different arcs. Here's one. Here's another arc. Here's another arc. Here is another arc. So I'm going to label the ends of the arc. So I have an arc from point A to point B. I have an arc from point B to point C. I have an arc from point C to point D. So that's this arc in black. And I have an arc from point D to point E. And this red arc from point E to A. So I have a number of arcs here. Just to remind some of you, a sector is essentially something that looks like this. It's something you can get from a circle. So you have a circle, you go to the center, you draw a line from this center to any point of circumference, and another line from the same center to another point of circumference. The region you form is a sector of the circle. But an arc is obviously formed. So an arc is always a component of every sector you form. Let me use a different color for that. So for this sector shaded in red, the arc is given in blue here. Well, you know what I mean. That's the arc. So now that you know what arcs are, and you know that sectors have central angles. So this is an angle here. I'll call that, I'll give you a numerical value. So I'm going to call this angle 80 degrees. I'll call this angle about 100 degrees. This angle, let's say, it's about 120 degrees. This angle is really small, so it's going to be something like 40 degrees. And this angle could be whatever it needs to be to give a complete revolution. But I just randomly assign this angle, so it's not to scale. But the main idea is, as you can see, this arc BC is larger than this arc AB. And that's because the angle formed at the center of this sector is larger than the angle formed at the center of this sector. So a better way to put it is this way, because this diagram is not to scale, but I just use this example here because you can clearly see that the arc BC is larger than the arc AB, and you can see that this angle of 100 degrees is larger than this angle of, well, you can tell 100 is greater than 80. So this is what I'm saying. I have a sector here. Well, this is a rough sketch of a sector. And there's an angle formed here. I'm going to call this angle 30 degrees. So it's a small angle. I'm going to draw a bigger sector, which is going to have a bigger angle at its center. Well, at the center of the circle the sector is from. This is another sketch of a sector. I'll try and do a better one. So you can accept that as a sector. This angle is clearly larger than that angle. I'll call this angle 70 degrees. The idea is as follows. If you think about it, if I'm moving from this point, I'll call this A, to point B, essentially covering an angle of 30 degrees about this central point, an angle of 30 degrees. Moving from this point, I'll call this A prime, call this point B prime. So moving along this arc from A prime to B prime, I've covered an angle in a rotational sense of 70 degrees. Clearly, as you can see, arc A prime, the length of this arc, A prime, B prime, is greater than the length of the arc AB. And the angle formed at the center of the sector that this arc belongs to is larger than this angle. So what I'm just trying to say is the larger the angle formed at the center of the sector, the larger the length of the arc. And we're going to use that to essentially make sense of the formula required to determine the length of an arc. So for a full circle, the perimeter, I'm just going to call that S, is equal to 2 pi r. If I just pick out any arc, so this arc A, B, it's also going to have, let's still use S, it's going to have a length, and that length is going to be less than this 2 pi r. It's going to be less than the length of, well, it's going to be less than the perimeter of the circle. So I'm going to write 2 pi r, but I'm going to multiply by a factor, this alpha. And this alpha varies from 0 to 1. Alpha varies from 0 to 1. So alpha is less than or equal to 1, or alpha is greater than or equal to 0. If you've done inequalities, you know how I go here. But just don't worry too much about notation if you haven't done inequalities. What I'm just trying to tell you is alpha varies between 0 and 1. Now, when alpha is 1, s is equal to 2 pi r. When alpha is 1, we have a complete circle. But when alpha is less than 1, so when alpha is between, say, 0 and, let's say, 0.99999, you don't have a complete circle, you just have an arc. So you have something like what we have from A to B, or something like this, or this, or this, or this, or this, but not a complete circle. So the length of an arc is equal to alpha times 2 pi r, where this alpha is theta over 360. Now, like I said earlier, when alpha is 1, what we have is a circle, a complete circle. When alpha is when alpha is less than 1, but greater than or equal to 0, or instead of writing this, I can say I'm just saying alpha is between 0 and, well, let's say 0.999. But you know what I mean. I'm saying alpha is between 0 and 1, but not 1. Because when alpha is 1, it's a circle. So when alpha is in this range, what we have is just an arc. And I'll show you shortly. So if alpha is theta over 360, that means s is equal to alpha, which is theta over 360, times 2 pi r. Now if you think about it, when theta is 360 degrees, a complete revolution, what's alpha? Alpha is going to be theta over 360, which is 360 over 360. I can put degrees if I want, but all this gives us is 1. When theta is 360 degrees, 1 has a complete circle, alpha is 1. The length of the arc form is actually the length is essentially the perimeter of the circle. But when alpha is less than 1, or let's put it this way, when theta is less than 360 degrees, alpha is going to be equal to some value, some angle over 360 degrees. Now let's say 350 degrees. You know that 350 degrees over 360 degrees is going to be less than 1. Try any other angle that's less than 360. You always find that the alpha will be, so let's use 20 over 360. You know that that's going to be less than 1. You can try with your calculator. So the main idea is when theta is less than 360 degrees, so if you're moving about a point and you don't complete a revolution, what you formed is an arc. And the length of that arc is given by this formula, where theta is the angle formed by the sector that arc belongs to. So, for instance, I have this arc here. It will belong to a sector like this. And this is the angle that is at the center of that sector. I'll just do another example. Let's say we start with a circle. This is a better way to visualize it. So let's assume we want to find the length of this arc. Arc A, B. Now I have a circle here, and this is the center. The sector that this arc belongs to is going to be the sector formed by joining this central point to the ends of the arc. It's a sector because the distance from this center to any point on the circumference like B is equal to the radius of the circle. So the distance from this point O to A is going to be the radius. And we have this arc here. So what we have in this region is a sector. So the angle formed here is what we're interested in. That's theta. So the length of this arc AB, so I'll write S AB, is given by theta over 360 degrees times 2 pi r. So all you need to remember is this formula. Now you imagine I picked another arc, call this arc from here C to D. The length of this arc is just given by, so it's SCD is equal to whatever angle is formed at the center. So I have to draw a line from this central point, same center of the circle, to the two ends. This is O, ignore the black O. From O to D, we have the radius. From O to C, it's also the radius. So this is a sector. This arc CD has a length given by, well, I need to determine the angle here. Let's say this angle is, let's say 60 degrees. The length of the arc CD is equal to the angle formed at the center of the sector that contains this, well, that this arc belongs to, divided by 360 degrees times 2 pi r. So in short, summary of this lesson is as follows. The perimeter of a circle is 2 pi r. An arc on that same circle is going to have a length that's less than this perimeter, and the length of that arc is given by theta over 360 times 2 pi r.
Now this theta over 360 value is always going to vary between 0 and 1.
So what I want you to do is do the following. Let r be 10. You know that pi is 22 over 7. So draw a table, just quickly, draw a table, and for different values of theta, so let theta be 10, 100, 200, and 360. So use those values of theta and determine the length of the arc.
Or rather, in fact, first determine theta over 360 in the next column,
and then determine the length of the arc. So when theta is 10 degrees, find theta over 360, find the length of the arc, and do the same for the other values of theta. So fill these in, and what you find is that this theta over 360 always varies between 0 and 1, and the length of all the other arcs will always be less than the length when theta is 360 degrees. What does that mean? It means that the length of an arc can never exceed the perimeter of the circle that the arc lies on. The length of this arc here can never be larger than the perimeter of the circle. It can only be equal to the perimeter of the circle. And that means the arc we're talking about is the arc formed when you cover a full revolution. So summary of this lesson is this equation. I know that this theta is the angle formed at the center of the sector that the arc belongs to. So do fill in this table, you learn something from it, and just remember this formula. That's a key takeaway from here. And obviously you already know what the perimeter of a circle is. If you don't know, keep this in mind, you need to remember it.